heavy class.
Say again?
Pretty heavy class today.
Pretty big class, isn't it?
Yeah.
Well, it's 8 o'clock and it's time to get started, so let's get started. Uh-oh, who's got a Valentine's Day?
I don't know, man. I said Peterson.
Oh my, that's right. No, it's only Valentine. It only just came Valentine's Day. That would be tomorrow that we would expect him to not make it to class. Anyway, all right, we have covered the inverse functions and the inverse trig functions last time. Do any of you have any questions about the inverse functions? Also, it occurred to me that we never did review the exam, so if any of you have any questions from the last exam, now would be a good time to bring them up. And if you have any questions from the homework, yes? I don't know, what's your name? Derek Heineman. Oh, let's see. Yeah, well, let's see here. Yeah. Okay. Did you get back all your homework yet? Yep. All right. Since I got it out, is there a Jared Robertson? That's you? There we go. You're welcome. Jeremy Reichert. Say again? Not here? Jacob Sanchez. That you? Yeah, I got a whole slew of stuff for you. There you go. Jory Owens. Jory Owens. Lauren Pendergrass. That's you. Oh. Stephen Turner. Okay. Now's another time I wish I had chalkboards. You just go up and do this and you get everybody's attention.
Oh, I think I'd have to leave.
All right.
I touched on that inverse stuff from the other day just a little bit.
All right. Well, I impact what I think is I plan on using today as a review day to go back and look at questions from homework, exams, and to review the material that we already covered. So, what was your name?
Matt Letney.
Matt Letney. Have I got anything that I haven't handed back to you yet?
No.
You're going to take the test? You want to do a makeup on it?
Yeah.
Okay, well now it'd be a good time to do that before we start talking about how to do it. No, ain't nobody getting that lucky. You need to redo your... Who else hadn't done the exam yet? Who else conspired to double up my workload this weekend? Put your hands up. How many do I need? 2, you, 3 of you? Somebody else? Anybody else? You got your... You can leave your books and your notebooks right here. Bring your cards and your calculators. And anybody else? All right, here. Before I make that thing nut up, I'll leave that right there. I'll be right back. Yeah, that would be fortuitous, wouldn't it? Sit in on a class where everybody else works all the problems off the exam and then you get to take. Okay, who has a question? Who has something they want to bring up to go back and look at? We can, yeah, it's all open. You have something off the test you wanted to look at? Given the function y equals 4 sine 3x plus 2. Can everybody read that? Okay, A. What is its amplitude? 4. B. What is its angular velocity, omega? 3. C. That's it. That's your angular velocity right there. And it's going to come into play in the very next part. What is the period of this function? 2 pi divided by 3. How did you know that? Say again? Omega, exactly. The period of the function, because it's a sine function, its normal period is 2 pi, and it's divided by this angular frequency, 3. So 2 pi over omega. If, a bit of a trick question, what if this instead of sine, what if it were tangent? What would the period be then? No. What is the base period of the tangent function?
Pi over omega.
It would be straight pi over omega, because the base, the period of the tangent function by itself, just normal, is pi. The period of the sine function is 2 pi. So what you're doing here is you're taking the normal, the unaltered period of the function, and dividing it by this angular frequency. So if it had been a tangent function up here, then the period would not have been 2 pi over 3, it would have been pi over 3, like you said. What is the domain of the sine function? Negative infinity to infinity. Now I'm going to bring out a couple of points on this because this is still eluding some of you. When you write the domain or a range of numbers, when you write a set of numbers like this using the set notation, the curved parentheses on the end means that that endpoint is not included. If the minus and plus infinities were actually included in the set, then you would use the square brackets to indicate that they are included in points. As in, right now, what is this function's range? What's the range of this y? Let's work through it and see. Normally, its range, if it were not offset with this constant, its normal range would be its amplitude times the normal range of the sine function. The sine function's normal range is, there's those square brackets, -1 to 1. But because this function has an amplitude, a non-unity, it's got an amplitude greater than actually anything other than 1, this range is scaled by that amplitude, so it becomes -4 to 4. If this is all we had to work with, just the 4 times sine 3x. But we don't. We've also got this offset. So you have to add 2 to both ends of the range. So when you take -4 and add 2 to it, you end up with -2. And then when you go to the other end of the range to 4 and you add 2 to it, you end up with 6. Everybody see how that works? So yes, you are quite correct. The range is -2 to 6. Now, here's one that still gets quite a few of you. What are the key points for graphing this function? Well, let's start with a normal unmodified sine function. Your first key point is 0, and the sign at 0 is 0. Okay? The next key point is 1/4 of the total period, which for a sine function, the total period is 2 pi. So 1/4 of that total period, 1/4 of that period, is pi over 2. So you go to pi over 2, and sine at pi over 2 is 1. Remember, pi over 2 is 90 degrees. Sine at 90 degrees is 1. The next key point is half, or 2/4 of the total period, which half of 2 pi is pi. And sine at pi is, once again, 0. Now we go to 3/4 of the total period, and we're at 2 pi over 3. I'm sorry, 2 pi over... there we go, trying to do arithmetic in my head again. The period is 2 pi. And 3/4 of 2 pi is, 3 times 2 is 6 pi over 4, which would be 3 pi over 2. So, we go to 3 pi over 2. The sine at 3 pi over 2 is Somebody say it out loud. -1. And then finally we go to 4/4 of the period, or the whole period, which is 2 pi, where the sign is, again, 0. These are the 5 key points for a normal, unmodified sine function. In this case, those key points are now, instead of taking 1/4 steps along the 2 pi period, we're going to take those same quarter steps, but along the period of this function, which is 2 pi over 3. So, well, it's still a sine function, so we're still going to start at 0. And the sign at 0, no matter what else you multiply it by, is still going to be 0. But now, what is 1/4 of that period? It's going to be 2 pi over 3 times 1/4, or 2 pi over 12, or 2 divided by 12 reduces to pi over 6. So the first period is pi over 6. And what's the sine value at the first key point? Still 1. Except now it's modified. So it's 1 times 4 plus 2. So when you multiply 1 times 4 and add 2 to it, you get the top of your range. It would be plus 2, yes. That's a good catch. Thank you. You still have to add that offset. Now, the next point, 2/4 times 2 pi over 3. Equals 4/12 pi, or 2/6 pi, or 1/3 pi, pi over 3. So we get pi over 3, and the sign is back to 0, but add the 2, and you get 2. The next key point is, that's 1/4, 2/4. The next one is going to be 3/4 of the period. So we're going to go 3/4 times 2 pi over 3. The 3's cancel. The 2/4 becomes 1/2, and we end up with pi over 2. Now we're at -1, but that's -4, to which we add the 2, and that brings us to the bottom end of our range, which is -2. And that brings us around to our final, which is the full 4/4 of the period, which is 2 pi over 3. And we're at 0 plus 2. And these are the 5 key points, which I can't see now, but we're still going to write them. 0/2, pi over 6, and 6, is it? And pi over 3. Next.
Pi over 2
and
pi over 3 and plus
2 pi over 3 and 2. And then it says, finally, we graph this function. So 1, 2, 3, 4. Here are our key points. Let's label them. 0 and plus 2. Yeah. 0, 2. Pi over 6 and 6. So this would be pi over 6 and 6. And then the next key point is pi over 3. And it's going to be back at 2. And then the next key point will be pi over 2. And minus 2. And then finally we go to 2 pi over 3. And our final point is 2 pi over 3 and 2. And to do the graph, you try to draw a lot smoother curve than I do. Bada bing, bada boom. Any questions about how we did that problem? All right. What about from the homework? Any questions from any other questions on the test that you wanted to look at? Or from the homework?
74.
74? Yeah. I'm going to find the exact solution of each equation. Okay. We're looking for the exact solution to 5 times the inverse sine of x minus 2 pi. And that is equal to the 2 times the inverse sine of x minus 3 pi. All right. Well, what would who asked for this one? You did. Okay, what would be the first thing you would think to do? I wouldn't, not yet. Yeah, let's see if we can rearrange this to make it a little more manageable. How about if we start by adding 3 pi to both sides? So this becomes 2 times the inverse sine of x, and this becomes plus pi, and that's 5 times the inverse sine of x. So we've got 5 times the inverse sine of x is equal to, plus pi is equal to 2 times the inverse sine of x. So let's subtract 2 times the inverse sine of x from both sides. We end up with 5 inverse sine of x minus 2 inverse sine of x plus pi equals 0. Well, 5 minus 2, factor out the sine of x, 5 minus 2 is just 3 times the inverse sine of x plus pi is equal to 0. So the inverse sine of x, or 3 times the inverse sine of x, is equal to minus pi. And if we divide both sides by 3, we have the inverse sine of x is equal to minus pi over 3. So if we take the sine of both sides, the sine of the inverse sine of x is equal to x. And that's equal to, what is the sine of minus pi over 3? Yeah, I don't have that much of the unit circle memorized either, so I'm going to find it right over here, and we're looking for minus pi over 3 is 5 pi over 3. Page 1, how about 179? There's one on page 190? Oh yeah, there it is. Sine of minus pi over 3 is minus the square root of 3 over 2. Okay. Let's test and see if we got it right. And multiply 5 times the inverse sine of square root of 3 over 2, the negative square root of 3 over 2, minus 2 pi, and 2 times the inverse sine of minus square root of 3 over 2, minus 3 pi. So let's get out our calculators. And did I bring my calculator with me? Guess I did not. Oh no, one of these. Okay. 3 square root divided by 2. Nope. And you know what? I'm not going to stand up here and figure out how to work this thing. So somebody who already knows how to work their calculator. What does the first side come to? What does this side work out to on your calculator? Error?
Yeah, I got error.
Minus 11 pi over 3. I like yours because I can remember that long enough to write it down. What did we get on this side?
That's another problem I run into is I know what time like a fraction. My calculator just put it in on me like a 11 pi over 3.
Okay, what does it give you?
I don't know, it gave me like 200 something, but that doesn't make any sense.
Well, what's 11 times pi? Would be, well, 10 times pi is 31.4 and change. 11 times would be that plus 3.14 more, so 34 or something. You got the same thing on this part too? All right. Well, we know that the sine of minus square root of 3 over 2, the inverse sine of minus the square root of 3 over 2 is going to give us minus pi over 3, right? And we multiply that by 5, we get minus 5 pi over 3. Subtract 2 pi from that. Here we get 2 times minus 2 times the square root of 3. Nope. Minus 2 times pi over 3 minus 3 pi. We can minus pi times 5/3 minus 2 equals minus pi times 2/3 minus 3. I'm sorry, plus 3, plus 2. So that's 2 is equal to 6/3, so 5 plus 6 is 11/3. So this side we get minus 11 pi over 3, and this side we get um, 2/3 plus 3/3 is 9/3. So 9, that would be 11/3 times minus pi. So minus 11 pi over 3. Whoever got that the first time got it right. Why was it important to go back and check our work on this one? Where was our biggest risk of making a mistake on this problem? Well, yeah, clearly the biggest problem a lot of us had was being able to punch the right buttons on the calculator. But just from a mathematical standpoint, what was the biggest risk in working this problem? What was the sneakiest little way it was going to sneak around behind you and bite you? No. What is the domain of the inverse sine function? The domain of the sine function is negative infinity to plus infinity. But what's the domain of the inverse sine function? Okay, let's go back up a little bit and ask the question, what is an inverse function? And what is the special condition that a function must meet in order to have an inverse function? Anybody? It has to be 1-to-1, exactly. Remember, the definition of a function is a set of ordered pairs where every x value gives you a unique y value. And that is true for the sine function, all the way from negative infinity to plus infinity. You put in any value of x from minus infinity to plus infinity, and it will give you one and only one unique value of y at that x. But it will give you an infinite number of x values for every y value you pick in its range. Okay, and that is the opposite of a 1-to-1 function. In order for a function to be 1-to-1, not only does it have to be a function in that every x gives you a unique value of y, it has to also have the property that for every value of y in its range, there is one and only one value of x that will produce that value. That is what is necessary for a function to have an inverse function, because when you do the inverse, the y values become the x values, and the x values become the y values. Remember, you're mirroring it along that 45-degree line of y equals x. So if, in its original form, it has multiple x's that give you the same y, then when you do the inverse, you're going to have multiple y's for every value of x. And then that means it's no longer a function. That's why a function has to be one-to-one in order to get an inverse. If we did the inverse of the sine function, what we would end up with is this. So for every value of x in its range, its range was -1 to +1. So now that's its domain, -1 to +1 inclusive. And for every value of x in that range, you're going to get an infinite number of y values. Okay? So, in order to solve that problem, we take the inverse function not of the entire sine function, but only from minus pi over 2 to pi over 2. And that gives us an inverse function whose domain is now -1 inclusive to 1, and whose range is now minus pi over 2 to pi over 2 inclusive. And that becomes the domain and range of the inverse function. So, where will we get it? Where was our greatest risk in solving this problem? 74, was it? Was making sure that when we started taking the inverse sine here and when we did this, were we still operating within the domain and range of the inverse function? Okay. Where were we at? Is pi over 3, minus pi over 3, is that in the domain or in the range of minus pi over 2 to pi over 2? Yeah, we were right down here at minus pi over 3. So we were good. But what if this had been, instead of minus pi over 3, what if this had been minus 6 pi or 7 pi over 3? Well, then we would have been down here somewhere, outside of the range of the inverse sine function. What would you get if you tried to take the inverse sine of 1.2? Somebody get out their calculator, type in 1.2 and then hit the inverse sine function. Error. It's exactly right. There is no angle that will give you a sine value of 1.2. That's beyond the range of its value, of the function. So you're never going to get an inverse sine of 1.2. When you do start using your calculator to take the inverse of these different angles, you're still going to get a value, but it's going to be somewhere within. You're going to get an angle, but it's going to be somewhere in that initial restricted domain of minus pi over 2 to pi over 2. And if that's not the actual angle that you were looking for, then you're going to run into difficulty. All right? That'll be a real problem for those of you who are in engineering majors or in engineering studies. You'll have to be very careful when you start solving AC circuit equations and looking for phase shifts and things like that. You gotta be careful about that sort of thing. Yes? 69? Okay. 99. 3 inverse cosine of 2x equals 2 pi. Okay, well, why do you want to change the number? Well, no, I'm serious. Why did you ask to change the number? Oh, well. Okay. Well, how about we work it the way it's written so we can use the answer in the back of the book to confirm that we did it right, and then then if we want to, we can go back and change the numbers. 3 times the inverse cosine of 2x equals 2 pi. 3 times the inverse cosine of 2x is 2 pi. Okay. What would the first thing you do? What would be the first thing you do? Divide both sides by 3. You end up with the inverse cosine of 2x is equal to 2 pi over 3. Well, let's start by asking ourselves, are we still in the domain and range of the inverse cosine function? What is the cosine of 2 pi over 3? Negative 1/2? Oh, that's right, 2 pi over 3. I'm thinking of the quaternal angles. 2 pi over, so that tells us that if we take the cosine of the inverse cosine of 2x and get 2 pi over 3, then that tells us that 2x is going to equal 1/2. 1/2 or minus 1/2? Minus 1/2. Okay. From this point, would you solve it? Divide both sides by 2. You end up with x equals minus 1/4. Is that what the book got? This part right here is where it's going to want to confuse you. When you get to the thing where you're saying, well, the inverse function of this gives me that. All that is saying, and everybody listen, pay attention. This might be kind of important for you. If this is a point in the solution where you start feeling confused, understand that all this is saying is 2x is the value that you will get when you take the cosine of 2 pi over 3. Okay? Like when you write the square root of x equals 5. What you're saying is x is the number you will get when you square the number 5. Okay? That's the other way of reading this. The inverse cosine of this value gives you the angle that the cosine of that angle would be the 2x. So you unravel it when you take the cosine of both sides. Because the cosine of the inverse cosine of 2x, well, what's the inverse cosine of 2x? It's the angle. So when you take the cosine of the inverse cosine, you end up with that angle. And that gives you the cosine of the number you're looking for. Or the cosine that gives you. Right there is where it gets critical. Is understanding what you're reading when you see that written. It says the inverse cosine of this number is that value, that angle. Remember, with the regular cosine, when the normal cosine function, you take the cosine of an angle to get a value of y. So when you do the inverse of that, you're going to take the inverse cosine of a value of y to come up with an angle. This is just going back to the whole domain and range thing gets flipped around. The normal function has a domain of angles and a range of y values. So the inverse function has a domain of y values that then give you angles as a range of angles. And what you need to make sure of is that the angle you're working with is actually in the range of angles that you're dealing with, that you're looking for. Now, you want to change the numbers and do this one again? All right.
Notice there's like a pattern, at least this bottom section. Can you just take, for instance, it's the inverse cosine? Can you just take, okay, so 2 pi over 3. So from the very top, you just take cosine of 2 pi over 3. Get that answer, which is 1/2, right?
Yeah, exactly. Cosine of 2 pi over 3 equals minus 1/2. Yeah, and then divide it by the omega from this. Yeah, that is exactly what you do. The steps here are not the steps here that you're going through to do that are what you have to do in order to make sure that it's legitimate to do what you're talking about doing. So let's change the numbers up. Let's say 5 times the inverse sine of 3x equals, okay, 4 pi. All right. First thing we want to do, we know that in order to get rid of this inverse sine function, we're going to have to take the sine of both sides of the equation. Well, if we just start off by taking the sine of this, then we're adding in another omega here, and we're just complicating everything. So let's start by getting rid of that. Divide both sides by 5, and we end up with the inverse sine of 3x equals 4/5 pi. Now, what is our range? What's our domain? The domain is going to be -1 to 1. The range is going to be no. Remember, minus pi over 2, pi over 2. Well, 4/5 of pi is outside pi over, is bigger than pi over 2. So we're outside this domain. Let's go ahead and let's keep that in mind as we go forward. Now, if we take the sine of the inverse sine of 3x, we can take the sine of 4/5 pi. So we've got 3x equals, what is the sine of 4 pi over 5? And this is why I wouldn't give you a pi over 5 angle, a multiple of pi over 5, because we don't know those exact values. You'd have to use, at this point, you'd have no choice but to use the calculator. Are you in radians? And it's what? Okay. 0.58. So x then would be equal to 0.58. What's that divided by 3? 0.0195? All right. Let's look at what happened here when we did this. Pi over 5, this would be pi over 6, pi over 4, pi over 3, pi over 2. So pi over 5 is actually going to be somewhere around in here. 1. 2 pi over 5 would be 1. It's going to be somewhere here. 2, 3. It's going to be, well, if it's 1/5 of pi, it's pi over 5 less than pi. So if this is pi over 5 here, 4 pi over 5 is going to be the same thing here. But the point is, it's beyond pi over 2. So if we're looking at it on this graph, here's minus pi over 2. Here's pi over 2. There's pi and minus pi. 4/5 of pi. 4 pi over 5 is going to be not quite, well, it's going to be about right there somewhere. But it's outside of it's outside the domain for the inverse sine function. So what would the actual sine at 4 pi over 5 be? Well, it's going to be 0 here, so it's going to be somewhere around here at that value. All right? Well, see, this is the x value that it's actually going to return. You just moved this point out here into this first principal domain. Y'all done?
Yeah.
Merci beaucoup. So, now, in terms of the problems here, what you have to be careful of is if you end up trying to take like the sine of something that's greater than 1. Okay, if you're trying to take the inverse sine of something greater than 1, you're going to get an error. You're going to get an undefined result. That's really, in terms of this class, that's really all you need to worry about. If you do take the inverse sine of a number, it's going to bring you back into this domain. Okay, so the only time that would be of importance to you is if you were actually wanting to find this angle, but you take the inverse sine of this value, it doesn't give you this angle, it gives you this angle. Do you see what I'm saying? Now, if you're an engineer, that might hurt you. If you're trying to figure out a vector, and the vector, if you're doing vector addition, and you're adding two vectors together, and the angle of the resultant vector is somewhere outside this range, then it's going to give you the wrong angle for that resultant vector. And that's when you have to be, like I've said, that's when you have to do the math. Just use the calculator for the arithmetic. And in order to do that, you have to understand what's happening when you take the inverse sine of an angle. Doesn't matter where on the line that angle is. It's going to bring you back to pi over 2 to minus pi over 2. In this case, you were taking the sine of this angle way over here, but the inverse sine function returned this angle right here. Okay? Anybody got any more problems or questions they want to ask about? Any homework problems? No. Well, I'm not much of a song and dance man, so I'm not wearing my tap shoes anyway. That's the answer you would put. If you take the inverse sine of 4 pi over 5, you're going to get the value of pi over 5 as your answer. Okay, but you have to understand why that is. If you were adding, in this book, in this course, that's the answer that they want you to get. They want you to know that, no, you're not going to get 4 pi over 5, you're going to get pi over 5. And that will be your solution. Where it would matter is if you were adding vectors. Say you were, let's say you found a resultant vector that gave you you found a resultant vector that ended up with components of, I don't know, say 7x or 7i minus 12j. And you wanted to convert that back into a single magnitude at an angle, a polar form. Well, you'd get the magnitude by taking the square root of the sum of the squares. That gives you the magnitude of the vector, but to find the angle, you would then have to take the inverse tangent of 12 divided by 7, which I don't know if that would fall within the range, within the proper domain of the tangent function or not, but if it's outside that domain, then it's going to give you an answer from inside that domain, and to get your proper angle, you would have to add 180 degrees to it, or subtract 180 degrees from it. But that's something that you would have to keep tabs on in your own head. The calculator is not going to do it for you. And that's the whole point of all of this that I'm trying to explain, is that the calculator is always going to bring you back to this principal domain. When you take the inverse sine, inverse tangent, inverse cosine, doesn't matter. It's always going to bring you back to whatever the principal domain is. For sine and tangent, it's going to be minus pi over 2 to pi over 2. For cosine, it's going to be 0 to pi. Okay? But there is that fundamental domain that the original function is restricted to ensure a one-to-one function so you can get an inverse function. Right? So every time you use the inverse of a trig function, it's going to bring you back to that original fundamental domain. Anything else? Any more questions, comments, parting jokes? That was not one of them. Well, then y'all have a good weekend.